you very much for your talk and overview of the latest progress in neutron star and gravitational wave. I am sure that Eugene would be happy to see that these results can be applied in many fields. So, and now after the particle physics and nuclear physics, I would like to ask the third speaker of this lecture, Professor Morten Krogh, and speak about
Princeton, where Eugene Wigner spent most of his scientific career, and he cancelled his arrival. And when I was asked, I had three motivations to say yes. One of them was that probably I was the only Hungarian from Hungary in 1963, working in Sweden that time, who was present at the prize award ceremony of Eugene Wigner. And when he learned that I am from Hungary, then he used all occasions to meet me, invited me to participate in all Nobel events, and we had very nice discussions, mostly on physics. And I have to admit that this very significantly influenced my scientific way of thinking. The other argument is that this June I had been invited to give a talk at Princeton University, by chance in the same lecture hall where Eugene Wigner used to teach his students. Finally, the third one is that I consider Eugene Wigner one of the heroes of quantum mechanics too, and he did quite a lot of things. We heard already about symmetry. In solid-state physics, we speak many times about Wigner functions, and there are many other things. I remarked with yellow on this transparency, one of them. I had a few years ago, many years ago, a discussion with him where we discussed the quantum Young experiment much earlier than the experiment was interpreted by others. And my talks is going to be connected to a certain extent with this yellow line. Another interesting thing is, and I think it will not be discussed here, is that especially at the end of his life, Eugene Wigner had been involved in thinking about the connection between human conscience and quantum mechanics. And he came to the conclusion that quantum mechanics cannot be understood without finding the correlation between these two things. Of course, this is still questions, but anyway, he had very firm views on that. My story starts a bit earlier. In the 90s of the previous century, I had the chance to work as a Humboldt professor in one of the Max Planck institutes, the Institute for Quantum Optics in Garching near Munich, where I developed a scanning tunneling microscope which scans the near field of surface plasmons. Surface plasmons are just polaritons, the marriage of electromagnetic field and conduction electrons of the metals on a metal surface, where the metal has a negative part of it, a real part of its refractive index, and these are waves of the electrons on the surface connected with the electromagnetic field above it. These surface plasmons have very interesting properties. For example, the well-known optical diffraction limit doesn't apply for them, and one can collect a huge amount of energy in very tiny sub-nanometer fields too. And therefore, in nanotechnology, this type of microscope is one of the potential microscopes of the future. In these studies, I could really find, for example, this is the image of a gold surface, which is 100 by 100 nanometer large. So of course, and it was excited by a helium neon laser. So of course, according to classical physics, you should not see anything. And you may see that there is very nice bumps on one of the on the upper part of this figure, and on the lower one you see the surface plasmons which get localized at these bumps. The field is enormous in such cases. I will give you a little bit later numbers on that. And this is again one potential source of applications. If we excite the scanning tunneling microscope with a laser and excite the surface plasmons, and you scan these plasmons with a scanning tunneling microscope, then you find that the response of the microscope is positive when the microscope is positively biased, and it's negative when it is negatively biased. But we found some places, some spots, which are marked on this upper blue image with black spots, where this response is much faster. Practically, it is equivalent to the resolution function of the microscope, and it is negative when the microscope is negatively biased, but it is still negative when the microscope is positively biased. And the reason is that the field of the plasmons, which gets rectified, by the way, is much larger than the field what you put on the microscope, which is a diode practically, where you put a bias on it. Now, if you look at the characteristics of this, you change the bias of the microscope, then you may see that, as you would expect in some cases, the curve is 0 when the bias is 0, but in these special cases, even if it is, you know, I have a problem because I don't see the red light. So in the lower curve, you may see that when the bias is 0, there is still a signal. So the surface plasmons are very strongly rectified. So the images what you can make with such a microscope, it are 3 images. The upper one is the topography. This is trivial. Below it is a thermal image, which shows the local temperature due to the decay of the surface plasmons, which in this case are, the lifetime is shorter than 100 femtoseconds. But the left side shows the image of surface plasmon fields on the surface. Now, if you make a Fourier transform of it, then the 3 images, 2 of them on the right-hand side have 1 peak. The surface plasmon image has 2 interference peaks on the side of the central peak. This peak is a very strange effect, because the intensity of this laser was such that at one time there was only 0.1 surface plasmons present on the surface. That means if this is interference, and I think it is, then only the plasmon can interfere only with itself. So this is the quantum Young experiment, and it was detected by this scanning tunneling microscope. But if we analyzed the surface, then it turned out that the thermal signal behaves as it should, so it is a Boltzmann distribution. But on the left-hand side, you may see that the dots are narrower than the full line. The full line is a Poisson distribution, so there is even a squeezing effect occurring in the surface plasmon field. So this was the first sign to detect that surface plasmons show non-classical properties. Although in such a plasmon wave, about 10 to the 11th, 10 to the 12th electrons are involved. So this is a mesoscopic system. But now I come to the real story, and probably many of you have experienced that the great things about physics is that it discovers things where you would least expect them to be found. Nice results usually come out at places where you don't expect them. At least that was my experience. So what we did, we succeeded to couple femtosecond laser pulses into our scanning tunneling microscope. Here I show the femtosecond pulses at different laser intensities, which you show that they are very nice. And one would expect that if you look at the response of the scanning tunneling microscope, then you would get a monotonous increase, and after that a saturation. This is coming out from a theory which was worked out by Keldysh in the Soviet Union many years ago, and proved, for example, by Győző Farkas and his group in the Central Research Institute for Physics at the end of the 70s by measuring electron emission from gold surfaces under very strong laser pulses, also that time much stronger ones. So the dashed line shows what I expected. And you see that an anomaly was found in the range, I don't know whether you see it, around 80 gigawatt per square centimeter laser intensity. So it's quite significant laser intensity. I didn't understand that. And by chance, a few weeks later, in Prague, I listened to a talk of someone who was involved in superconductivity and made a trivial statement mentioning that, as we all know, in a superconductive state, the probability of tunneling is decreasing. This is a tunneling device. Wouldn't it be the case in our situation too? So when I returned home, we analyzed our measurement, and it turned out that the tunneling microscope responds to laser excitation as a function of laser intensity, started for about 20 microseconds. This is the resolution of the microscope, but increased up to 60, and after that, when further increasing the laser intensity, it started to decrease, and then increasing again. One measurement is not really a measurement, so we have a traditional technique in the Wigner Center, in the Solid State Physics Institute, and this is to measure the emitted electrons from Earth's surface like Győző Farkas did it. Already at that time, I had the idea that surface plasmons must be involved in this process. So what we found by analyzing the emitted electrons by time-of-flight spectrometry, now on this upper left curve, you see as a time dependent, so not in energy, that there are 3 peaks in the spectrum, and the different lines are in different laser intensity, but there is a small peak on the left-hand side. And if we analyze the intensity dependence of these 3 curves, then it turned out that the 2 slow curves, that means the right-hand ones, behave like predicted by Keldysh, and the left-hand side, small peak, behaves like the STM, like the scanning tunneling microscope curve. This is the right lower curve with a maximum and then decreasing. The only difference is that in the upper curve, the difference is a factor of 3. In the lower one is 3 orders of magnitude. It's a logarithmic scale. So, and then it came out into our mind, publication. Here you see it in 3 dimension. You see that on the left-hand side, the small peak. And it turned out that in the early 80s, 3 of our colleagues, 2 from the Solid State Physics Institute and 1 from Russia, published a paper studying the interaction, János Bergú, Sándor Varró, and Misha Fyodorov, who studied the interaction, the scattering of electrons on electrons in very strong electromagnetic field. Although we don't have in a vacuum, we have a neutral plasma in our case, but we supposed that the field, which is noted by F in this mu, is increased by the plasmon amplification, and we put it into this interaction potential, effective interaction potential, which of course has a Coulomb part and a Bessel function part. And if we calculate it for our case, then it turned out that at lower laser intensity, this function is always positive, but there are places where the function is negative. And the conclusion is that when this function is negative, then the electrons get paired, like in the superconductive Cooper pair case. And another experiment, of course, if it is by chance superconductivity, then the material should be ideal diamagnetic, so the Meissner effect should be seen. Magnetic field has to be applied. We measure time of flight of electrons. We can't put an external field because it spoils everything. So we use the magnetic field of the laser excitation itself by changing the polarization. Surface plasmons are excited in so-called p-polarization when the electromagnetic vector is perpendicular to the field and the magnetic is in the plane, which does not have any influence. But if we change the polarization angle, then there will be a perpendicular component which should influence. So if the spectrum remains unchanged, then the magnetic field is not there. If the spectrum changes, then the magnetic field is there. So what we analyzed, and it is seen on this figure, that when we measured at intensities in the maximum, that means 80 gigawatt per square centimeter, then of course, when you change the polarization, then the perpendicular field decreases. So you move on left-hand side of this resonance curve.